Good morning. My name is Greg Carlson. I'm president of NYARM, and I'm very happy to see everybody here on this important subject. And with that, I would like to introduce to you the executive director of NYARM, my good friend and the greatest executive director, Margie Russell.
Thank you, Greg. Good morning, everyone. My name is Margie Russell, and I'm the Executive Director of NYARM. But now, let's give a rousing applause for Valentine Lair, professional engineer with Lair Engineering. Valentine, all yours.
Thank you, Margie. Good morning. It's always a pleasure to be asked to say a few words at NYARM, and I'm really delighted to be here today. The title of the talk here today is, What Do You Need to Know About Cooling Towers? And I hope that when I get finished speaking, either one of two things will have happened. Number one is that you may have learned something, however little, that you didn't know, or alternatively, that you've had a really good nap. So whichever it is, let's proceed and see where things go. So, cooling towers in the news. Well, certainly the whole question of Legionnaires' disease came up, and it came up with a vengeance in June and July, when we had a major outbreak of Legionnaires' disease in the Bronx. And the Legionnaires' disease phenomena seemed to spread. It got to more and more buildings. We wound up having quite a number of fatalities. I believe it was more than 10 people and quite a bit more who succumbed to the disease. So the question that we really have to start with is, what is Legionella? Well, interestingly enough, Legionella is a bacteria. And so it is the bacteria that causes the problem. And more importantly, it is not something that's unusual and that is rare. It is extremely common. Legionella bacteria can be found in soil, in aqueous environments of all types. You find it in water supply that's not properly treated. You find it in fountains, in ice machines, in any number of areas. And certainly you find it in cooling towers. And in that aquatic environment, what is actually happening is the Legionnaires' disease, under the right conditions, are growing. And if you combine that with a mechanism which allows it to be spread through the air, you have the ingredients which lead to an outburst. And so Legionnaires, 50 different species. There's a lot of more detail that you can find if you do a little bit of research on it. But more importantly, as far as the disease is concerned, it happens to be something which is spread by airborne transmission. And on top of that, the inhalation of the material is really what causes the problem. As an aside, it's very common. And in many instances, we all have inhaled it, and nothing has happened because it is most devastating to people who have already got an impaired immune system or problems with their lungs where it really takes hold. So if you are in really good health, there is a good possibility that even inhalation isn't going to lead to a problem. On the other hand, if you do have some problems, particularly heavy smoking and other things, it can impair your lung system. That's where the problem occurs. So, if we're going to talk about Legionnaires' disease, the recent outbreak and the legislation which is now facing us, the first thing we ought to do is to talk a little bit about cooling towers and essentially what they do and how they work. So the diagram you see up here is actually a profile through a cooling tower. We'll talk about different types of cooling towers later, but generically you can see what's happening. You know, an air conditioning system like the system that's serving this space here today has as its objective to take the heat that is in this space, that's the heat that comes from the light, the equipment, the people, and the outside air which is brought in for ventilation, and we got to get rid of it. We have to eject it from the building. And there are several steps along the way. We pass air over cool coils. So now we extract the heat from this space and we put it into the water. The water goes to a refrigeration machine. That refrigeration machine transfers the heat from the water into the condensing system. The condensing system is, in the case of water-cooled systems, the cooling tower. And so if you take a look at this diagram, you can see that what's happening is the chiller is transferring hot water into the cooling towers. It goes through a distribution pan over here. That water allows, that distribution pan allows water to drip down through the fill material in here. At the same time, air comes in and is drawn across. And so what's happening is the air is moving across the falling water, and that's promoting evaporation. With the evaporation, the heat energy is distributed into the air. And the cool water comes back, and we do it again, and over again. So the way a cooling tower gets rid of the heat is through the process of evaporation. Now, when water evaporates, there's a whole variety of things that happen. So, for example, water contains solids. It contains potentially bacteria. As that water evaporates, those solid materials and the bacteria particularly are dispersed with the air. So in a cooling tower, you've got lots of air. There are several hundred CFM of air per ton in a cooling tower. So you're blowing a lot of air around, and with it you are potentially taking the Legionella bacteria and dispersing it. If it's dispersed into an area with a lot of people, heavy concentrations, it is the ingredient for Legionnaire's disease. Now, as I said, there's lots of places where water is used in ways where you could, for example, have additional spreads. Like, for example, you go to a fountain. My office is up 6th Avenue over here on 50, we're on 55th Street, between 54th and 55th, 1345 Avenue of the Americas have these beautiful fountains. And those fountains are a delicate spray, and when air blows through them, they disperse all over the place. You can make everything wet. And there's a lot of effort in that particular building to make sure that the water is bacteria-free, so it doesn't spread disease. But if you begin to take a look at cooling towers, it happens to be the largest and most common source of Legionnaire's disease. So let's take a look at this table. This is a very interesting table because what this is showing is the survivability of Legionella at different temperature ranges. So you see at the bottom, even in a frozen state, bacteria can go into hibernation and survive. And as the temperature begins to rise, they become a little bit more active and they tend to grow. At the top end of the scale, you see that above 70 degrees, you really kill it all. In the higher temperatures, you can kill the bacteria off. But in the range of 90 degrees to 108 degrees, it is the ideal growth range for Legionella. And guess what? That happens to be the range that most cooling towers work in. We look traditionally at cooling towers where we are running water from, for example, 95 degrees entering water and 85 coming out, 100 degrees going in and 85 to 90 coming out. So we're operating in the ideal range for growth. And so if that growth is occurring, it's being promoted by the mere operation of the cooling tower. So that's the reason why cooling towers happen to be the #1 vector. It isn't the only vector. In the original outbreak in 1976 in Philadelphia at the Stafford Plaza Hotel, there was a lot of speculation that it had to do with people taking showers. And indeed, if you take a look, there's a lot of regulation about the temperature of hot water. The idea being that the hot water should be hot enough in the 120 plus range in order to kill the bacteria. But again, it was with all engineering situations, we get into this dichotomy of the ideal range is we should kill everything at 125 degrees, but you know something, once we get over 120 degrees, we have a real serious problem of scalding. So do we risk scalding, or do we risk bacteria growing, and do we risk Legionnaire's disease? And what happens, do we have Legionella growing in shower heads and what have you? So these things are of concern, but as you'll see later, all of this is really addressed by a number of issues which are relatively simple and straightforward. So in any event, the reason why cooling towers are the main vector is because of what you see over here in red, because we're operating in the ideal growth range. So let's talk a little bit about spreading disease. Last night, I had the opportunity of going out to dinner with my wife. We went to a nice restaurant, and I certainly had a wonderful meal, and I trust that that meal was served from a really clean kitchen, like the ones you see on the screen over here. Because when you have a clean kitchen and pay attention, the possibility of all of the food poisonings and distresses of the stomach and intestines that one can have from bad food are absolutely kept to a minimum. On the other hand, I've been to a lot of restaurants. We did a lot of food service facilities, central commissaries, all sorts of things. And, you know, I've seen a lot of kitchens where these kinds of scenes were common. And in that kind of an environment where bacteria can grow and distribute itself, you have a real probability or possibility of getting disease, of a spread of bacteria, a whole variety of maladies. So conceptually, clean is good, dirty is not. And that isn't so different if we begin, by the way, if anybody would care to have a dinner in this place, I can recommend a couple of places to avoid, but what have you. So the same environment is true and the same reality is true for cooling towers. When we look at cooling towers, what we hope to see is a nice clean cooling tower, clean water going through it, no corrosion, dirt, slime, sediment, biological growth. You know, the water isn't green, it's nice and crystal clear. But the reality of the situation is that very often we see this in cooling towers. And these are situations where we have growth, we have dirt that's built up, the dirt is moist, it's an ideal bed for the growth of bacteria. This lower picture is quite an interesting one. You notice all of the foam in here. The foam is because the solids content of that water is far too high, and it is foaming. You can see the slime that's in these over in here. You can see the quality of the water over in here. This is reality for an awful lot of cooling towers that haven't been properly maintained. And if we are looking at the vectors here that produce Legionellas, you can see very simply that if you have an environment which is conducive to the growth of bacteria, the bacteria will grow. And if it grows, it is in an environment where it can be drawn through and dispersed by the air. So what we really need to do along here is we need to make sure that the cooling towers are properly cleaned. And along those lines, a regular program of cleaning is what is called for. And you can see these are before and after pictures of the same areas where this is what the fill looked like in a cooling tower before and after. This is the internals. You can see the quality of the water. You can see the projector here isn't really good. The actual photo showed a lot of slime in this area, but you can see how clean it is over in here and the quality of the water. So basically, the point is, what we have to do, and the number one thing we have to do, is make sure that the cooling towers are properly cleaned. Yeah. Well, Well, we'll get to that in a little bit later, okay? There's a lot more on the detail. Okay, so the point to remember, and I think this is important, is that organic sediments, scale, inorganic precipitants provide Legionella with an ideal surface for biofilm formation. Okay. So obviously keeping the cooling tower clean is an absolute essential. Now, if we take a look, there really, cooling towers come in a lot of varieties. There really are only two basic types of cooling tower. The first is what is known as a counterflow tower. And you can look at this diagram here and see that essentially air is going up and the water over here is going down. So a counterflow tower shows the water dropping down by gravity, and counter to that, the air is being forced upward. Remember, what you're trying to do with a cooling tower is to establish evaporation. And the more air that passes over the water, the finer the droplets of water, the more evaporation you have, the more effective the cooling tower gets to be. The other variety is called a cross-flow tower. And basically, in a cross-flow tower, water is falling down over here, but air is coming in on the side. And so now you have water dribbling down, but the air is blowing across it. Those are the two types of towers you have. What's the difference? Well, in terms of the ultimate effect, evaporation, there's no difference. In terms of the technical aspect of it, there's a lot of difference, and there's a lot of very specific things that are of interest to engineers. For example, is the height of the cooling tower and how that fits in with the aesthetic of a building. There's the approach temperature, that is how cool you can actually get the water. There is the amount of energy that has to be put in, the pumping requirements for one tower versus another, the airflow requirements, the fan horsepower that's required, the construction details. All of these things are factors that are of keen interest to the engineers who are designing it, because obviously, if the rejection part of the system doesn't work, the whole air conditioning system doesn't work. But in terms of what is needed to be known from the day-to-day operation or from the ownership point of view, it really doesn't mean much one way or the other than to note that there are these two types of towers. So what kinds of tower configurations do you have? Well, I'd like to show you a few of those. This is the typical tower configuration. If you go on any high-rise building here and start looking down, the cooling towers you're most likely to see are cooling towers that look like these two illustrations. The one that has a bit of a V shape, obviously what you're looking at here is a cross-flow tower, right? The air is coming in the side, the water is going down, there's the fan discharging. And this type of thing, which looks like a box, this could be cross-flow or counterflow, really can't tell from the outside, but this is the configuration that you most often see for cooling tower installations in New York City, all right? If you were in Southeast Asia, in Africa, in the Middle East, in Australia, the most likely type of tower you'd see is this type of tower, which is a circular type of tower, as opposed to the rectangular configuration. Some of them are very squat like this one, some of them are quite tall. Most of these are made out of fiberglass to avoid corrosion. And most of these are set up so they're done on a modular basis, and they are very easy to install. That type of tower, I do work all over the world, and we do certainly a lot of work in Asia and Pacific and Africa, Central Europe, and all over the places. You find this a lot. And these towers are really quite good. The fiberglass type tower, there was an attempt to introduce it here quite a number of years ago. There were a couple around, but the fiberglass ones, there was a lot of issue with regard to the flame spread and smoke generation potential of the casing, and it has never really taken hold around here. We still are in this type of thing. But again, these are the smaller range. This is, a couple of 100 tons worth of cooling tower, but there are a variety of others. I mean, clearly, you have to take a look at this one. This is a cooling tower, and basically, it's made out of ceramic material. And the ceramic material is built in the field, and it can be built in any shape or any form. It can be a decorative element. We did a very interesting project in Malaysia several years ago, a very hilly area outside of Kuala Lumpur. There's an area called the Damansara Hills, and the Damansara Hills are quite hilly. We were looking at a site for development, and we're trying to find a location for the cooling tower. The roads sloped down rather radically, and what we thought was the land formation was such that the roads were down high and the land was very low, so they were putting retaining walls in. So our cooling tower is the retaining wall. And essentially, we have a retaining wall that's porous on the roadside, and behind it, we have a ceramic cooling tower, a different variation with the fill in it. The air is drawn in off the roadway, the water is transported down, the air discharges up, and essentially, what happens is we have an invisible cooling tower. We have used ceramic cooling towers in any number of variations where it is difficult to place a conventional cooling tower. So you can build a cooling tower in any shape. And here you see it as a circular shape. This one happens to be extremely tall, but we've done the things as triangles. We've done it as a literal piece of artwork. So that's another type of cooling tower. Has the same effect, has the same problems. Is a little more expensive to build, sometimes a lot more expensive, but it has the ability to blend in unusual circumstances. You're all familiar with these. These are also cooling towers. These happen to be hyperbolic cooling towers. These are the cooling towers that are used for huge power plants. We don't see too much of them around the New York City area, mainly because we have a lot of water, read Long Island Sound, the Atlantic Ocean, and the rivers, where we can reject the heat. But you find these all over Europe. You find these over in the middle of America as a means of rejecting heat from large power generating plants. And the difference between that type of tower here and all of these others is these depend on fans to draw the air through. A tower like this could be 150, 200 feet tall, and basically as you blow hot water in, the hot water heats the air, causing the buoyancy of the air, causing an airflow up just like a chimney, and it operates without a fan. And so consequently, there's a significant saving in energy if you have a big enough load and if you have a site where you can have a cooling tower that's 150 feet or 200 feet tall. By the way, as an aside, there's a technology now which enables engineers to tap into high temperature at in the ground. If you go down 2,000, 3,000, 4,000 meters, 4,000 meters is roughly 13,000 feet, something in the range of 2 miles, 2.5 miles. You get extremely high temperatures, and this technology brings the heat up to the surface. And so you can imagine in a creative way that if you took a tower like this and you applied the heat at the bottom, that the heat would cause a huge updraft. And if you put a series of fans in, either here or up in here, you could generate electricity out of it. So it is an innovative way of taking geothermal energy and using it directly to induce an airflow which runs through wind generators. And those wind generators literally have the ability to produce significant amounts of power. We're talking about megawatt range electrical generation. And then finally, a simple fountain like this, and you've seen these, are excellent cooling towers. And there are any number of projects which we have done where we have large bodies of water. We put in spray ponds, spray facilities like that. If you are spraying warmer water into the air, as it comes down and the wind blows through it and the evaporation occurs, it cools water. And so it is possible to have the effect of a cooling tower from something that looks very natural, okay? Spray fountains also have the potential for having embedded Legionella bacteria and for spreading it. So that's one of the reasons why spray fountains in the middle of a city have to be dealt with, because of the possibility of doing that. But remember, a spray fountain has a much lower temperature range, and so consequently the ability to breed bacteria is significantly less than a cooling tower where the temperature ranges are much higher. Okay? So that is essentially a little bit of an idea of how a cooling tower works and what it does. All right. Next we get to the subject of cooling tower water treatment. Well, we have to keep the cooling towers clean. We have to avoid a variety of potential problems. So let's look at that for a minute. Obviously, cooling towers use water. And we can, look at water as the magical compound. We need it to live, It's a universal solvent almost. Pure water, absolutely pure water, is highly corrosive. Water, when we find it, generally has in it dissolved minerals, dissolved gases, and that defines the taste of the water. It defines the ability of the water to either be neutral or to scale or to corrode. And so consequently, what we really need to do is start with an understanding of the basic chemistry and nature of water, right? And also, a cooling tower gets its value in the air conditioning, if you will, from evaporation. That's the mechanism for the cooling. Now, if you have water that has solids in it, and you begin to evaporate the water goes away, but the solids stay behind. The easiest way of seeing that is if you have, for example, a clear dish, and you put some salt water on the beach on it, and you let it evaporate. The water evaporates, and you have the salt left over. Well, the solids in water act the same way. As the water evaporates, the solids stay behind. And so consequently, as you are continuing to evaporate, you're building up higher and higher solids. And those solids, if they are not properly controlled, have the ability to begin to scale. And so you have to deal with that issue of scaling and what have you. So the objective here is that you want to have clean water. You want it to be neutral, that is to say neither scaling nor corrosive. And basically, the water treatment program has got to be able to do that. And it does that with chemical treatment, adjustment, for example, of the pH is one of the philosophies that can be followed. There's a whole series of chemicals that are added, which are corrosion inhibitors. There are a variety of other things that get done. But it really gets down to the treatment philosophy. Now, there's lots of different approaches to chemical treatment. And I'm not here to tell you how to do it, because there is no how to do it. There are varieties of approaches that really depend on the quality of the water you have, the environment you're dealing with, and a whole variety of other factors. So there are different approaches that go with it. But essentially, what you're trying to do is to circulate water in such a way that it achieves the objective of proper heat transfer. You don't want the water to corrode your piping away, and at the same time, you don't want deposition of solids, scaling, because among other things, when you put that scale on, the heat transfer is really impaired, and your air conditioning system doesn't work because the tubes are all fouled. And so consequently, generically, if you talk about it, you can have a water treatment program which treats the water so it is just on the edge of corrosion, but it doesn't corrode. Or you can treat the water so it's just on the edge of deposition or scaling, but it doesn't scale. There's different philosophies. There are other newer approaches to water treatment. But objectively, what you've got to do is you've got to have the clean water, it has to be neutral, and it has to not impair the overall objective, which is getting rid of all of the heat. So along those lines, there's a lot of treatment programs. We'll talk about that in a minute. But essentially, you also have to be worried about the aspect of biological control. The biological control is slime, bacteria, and organic sediment. The issue of bacteriological control is not only killing off bacteria like Legionella, but also avoiding the slime, because slime actually can deposit on the interior of the tubes in a refrigeration machine, and it too really inhibits the heat transfer. And so if you have a slime buildup on tubes, you have less ability to reject heat and consequently less ability to do air conditioning and lots of complaints that go with it. And with regard to the biological treatment, as you know, if you take a look at many of the wonder drugs that have been used and have been discovered, we find that there is a bacterial resistance to the various drugs, and a lot of drugs that were wonder drugs 25 years ago are useless now because the strain of bacteria has grown resistant to treatment by those drugs. The same thing is true in biological treatment. One of the things that we've found is that if a water treatment program is not changing the biological treatment chemicals on a regular basis, what happens is that the bacteria become resistant to it and its effectiveness drops off. So the point here is very simple, that water treatment is not a static thing. It's something that's dynamic, conditions change, and the approach has to be adjusted in an overall comprehensive manner so that it achieves its objectives. And the last thing is the fact that there's a lot of war stories to be told about chemical treatment. You know, if you buy a chemical for the sake of anonymity, I'll call it Schmuckerklop 500. You go and buy a barrel of Schmuckerklop 500, this magical water treatment program, and it costs you a bundle, you know, and the water treatment guy tells you, hey, this will take care of everything. And you open up and you look, it's got this greenish orange color to it, and it smells awful, so it must be good stuff. You don't know what you're buying. And the interesting thing is, if it's injected into the system and it doesn't work, it's probably 2 or 3 or 4 years before you really get the effect of what this thing hasn't done for you. There's lots of stories to be told about water treatment. The bottom line is, deal with a reputable company. If you're dealing with a reputable company and they have a reputation and they can demonstrate that they've done the right thing in many instances on a consistent basis, you'll be fine. But beware of the discount guy who's going to sell you the miracle chemical, and because you don't know what you're buying. I think that it's extremely important along those lines. So in water treatment, you know, there are a bunch of things. It depends on water chemistry. There is something that's used widely, not by everybody, called the Langelier Stability Index. Now, I use Langelier, this is the English pronunciation. If you go to Europe, it's the Langelier Index. So if you really want to be fancy, it's Langelier Stability Index. But that's a calculation which tells you, for a given temperature, pH, solids concentration, pH, the calcium concentration, whether a water will be neutral, whether it will scale, how much it tends to scale, whether it is corrosive, how corrosive it can potentially be. And so with that information, the water treatment person has the ability to do the necessary chemical analysis to determine the best treatment program for the objectives of clean water that's neutral, isn't going to scale, and isn't going to have a biological growth factor that goes with it, right? And the water treatment, again, it's got to take care of corrosion, scaling, biological, and fouling. In this over here, that's just an example of corrosion. In this particular case, even though the pipe on the outside looks as though it's badly corroded, it actually is corroded mainly from the interior. Here's an example of scaling. You can see the scale buildup on the inside of the pipe. The net effect is that the area for the water to flow is significantly reduced, and that has a hydraulic negative effect of less water. Less water means less ability to reject the heat. But if that were a tube, the heat transfer to the exterior copper over here was very, very good. But when you add the scaling to it, the heat transfer is practically nothing. This is just, this is a tube bundle, and the man has just put his finger in the tube, and that's the slime that we talk about. And even though that doesn't look, I mean, it doesn't look particularly good, I wouldn't want to take it to dinner. But on the other hand, the heat transfer of this has been really impaired. So what we're trying to do is we're trying to deal with issues like that. All right, so we learned a lot about cooling towers and the water that goes with it. But you know, there are alternatives to water-cooled equipment. And what you're looking at here is air-cooled equipment. And this type of equipment actually has the compressors down here, and basically, instead of rejecting the heat through the condenser water circuit, it takes the refrigerant and it runs it through a series of coils, and they takes that and it rejects the heat directly to the air. There's no water that's required. And these are just a few varieties of air-cooled refrigeration machines, air-cooled package units or air-cooled chillers. So there is an alternative. And, you know, this is widely used in areas where there's no water. And when we work, for example, in the Mideast, there's no water. Well, water is extremely rare. So what happens in that particular instance is we are driven to air-cooled equipment. So why are we messing around with water at all? Why don't we just go to air-cooled equipment and avoid all these problems? We don't need any chemical treatment. We don't need to worry about Legionnaires' disease. We don't need anything of that nature. Well, here's why. What you're looking at here is a chart. This comes from the ARI, American Refrigeration Institute. And what it does is it explains the energy requirement for air-cooled versus water-cooled equipment. And what's really interesting in here is that if you take a look at air-cooled equipment, this is the best available. And you can see that the amount of energy that's required here is about 0.8 kilowatts per ton. Okay, that's interesting. But now take a look at that, because that's the equivalent in water-cooled, and it's about half. Now, this particular chart is an average of a wide variety of situations. It probably is not exactly indicative of the situation you'd find in New York City. But in general, the reason we use water-cooled is because it is a very, very much more efficient way of getting rid of the heat. And the reason for that is that if you are rejecting heat by air-cooled, and you have a day when the temperature is 90 degrees, the heat rejection is much more difficult because the rate of heat rejection is a function of the difference of temperatures. And when you have a much higher air temperature, the heat rejection is just more energy consuming. A cooling tower, by evaporation, lowers the water temperature below the air temperature. And so we're dealing with a situation where we have a much lower temperature and a much better heat transfer in the system. So the reason why water is such a wonderful way of doing things is because of this over in here. And if we take a look, I mean, whoop, I've got to go back one. If you take a look at this, I mean, this gives you an idea of the rating of the kilowatts per ton and where it is. In the water-cooled, we're down here and lower. In the air-cooled, we're up over in here. And this chart is not based on New York City electric rates, but is, again, indicative. This happens to be a 100-ton chiller. It happens to be part-load condition. And basically, you can see that if you've got a chiller, in this particular example, that's operating at a half a kilowatt per 0.5 kW per ton, it's $18,600 a year. Double that to 1, and it's $37,000. Now, in New York, these numbers, the spread would be much higher because of the extremely high cost of electricity here. But it happens to be the reason why we are so enamored, particularly in operating costs, with water-cooled equipment. And, you know, in those areas where we have not got a lot of fresh water, we still like to use water-cooled equipment. And what we do there frequently is we capture every last drop of sewage and treat it to the point where it can be reused as makeup water, gray water, in a cooling tower. And it's worth all the effort of recovering. And the reused gray water is particularly good, although gray water always has a higher solid content than a freshwater supply. Well, not always, but mostly. And basically what happens is you have to reject a little bit more of water in terms of blowdown, which is what you use to control the solids content. But in essence, what happens is that we try to work with that as much we can. So the next, we're getting to the end of this. I hope I am keeping you awake anyhow. this thing uses water. Just wanted to give you an idea of how much water. So I chose 100 tons because the other example we just looked at, it was 100 tons. And for a 10-degree temperature differential, we're circulating something like 300 GPM. Excuse me. Time for a drink. Thank you. So, so we're using about 300 GPM. I'm using here an evaporation and drift makeup rate of 2%. There'll be a lot of people who can argue that's too high, that's too low, or what have you. But for the purposes of what we're doing here, we can use a 2%. So that means the peak rate, when we're running at 100 tons, we are using 6 gallons per minute of water. And if we have operation from 7 in the morning till 6 at night, that's 11 hours. And clearly here we're dealing with an office building, not a residential or hotel structure or a hospital structure. And a daily load factor of 0.75, which means we're not operating 100 tons, that's the peak, continually for 11 hours, but the average over the 11 hours is 75%. We need about 3,000 gallons a day of water. All right, at New York City rates, if you meter it separately and deduct the sewage charges associated with the water, and that's probably around $4.50 or $5 worth of water. But if you are cutting your electrical consumption in half, you can clearly see that the extra cost of water is a bargain compared to what the electrical saving is associated. All right, and then just a few other things about cooling towers. Number one is undersizing is a big problem. A lot of people, cut back on the capacity of a cooling tower. If you cut back on the capacity of the cooling tower, 2 things will happen. One is the electrical consumption will go up as the machine works harder to reject the heat. And number 2 is you will have a drop off in capacity. It simply is not a good idea. Providing a little extra capacity on a cooling tower has the ability to bring the water temperatures down cooler, and you get with extra cooling tower capacity the benefit of improved operation, which means you're ensuring that you have the full capacity, but more importantly is you're dropping off on the electrical supply. So basically, a little extra cooling capacity doesn't hurt you, and it also gives you flexibility for something in the future, like somebody decides that they want to have a little bit of a data center and they need some additional cooling, and you have that. These days, cooling towers have come with a variety of things, and one of the things we are very much looking at these days is variable speed fans. So we can optimize the amount of air going through the cooling tower to what's needed and save on the fan horsepower. Almost invariably, a variable speed fan on a cooling tower will pay for itself in a period of 18 months to 2 years. And also, given the restrictions on flow through machines, which is a technical discussion we don't need to get into now, we also have been looking at variable condenser water flows in order, again, to optimize the cooling tower performance. And what's the life expectancy of a cooling tower? Well, the government will tell you that it should be written off in terms of depreciation in 15 years. And you almost always have a life of at least 20 years on cooling towers. I have seen cooling towers that have been properly maintained that were installed over 40 years, and they're working just fine. One of the first jobs I worked on back in antiquity, when I was a mere child, was the Sealand Services facilities over in Port Elizabeth. And I'll give you a hint, it was in 1965. I recently had occasion to go over to take a look at one of the buildings I worked on in 1965, and that building is still there. It has every piece of original equipment, including the cooling towers, and they're working just fine. The refrigeration equipment is obsolete, and the efficiency of it is just absolutely awful, but it works and it looks like it's brand new because of the high quality of maintenance. So you can get a tremendous life out of a cooling tower. And let me end then with just a couple of 2 quick thoughts. there's some creative things you can do with cooling towers. Like, for example, if you've got a cooling tower, you can go and modify it, because in the bridge months like we're coming into now, in the autumn, in the winter, in the spring, you can produce water temperatures off a cooling tower which are cold enough to drive your refrigeration requirements in the building without ever running the chiller. So essentially, all you need to do is add a heat exchanger and take the cooling water from the cooling tower, run it through the heat exchanger, and it will operate the cooling load of the building with the chiller in the off position. And that's something that we've been doing for 30 years. But it's surprising how many buildings that are here that run a cooling tower all year long in conjunction with a refrigeration machine, when some sort of modification like this has extremely, extremely quick paybacks. And another thing is double service. You know, a cooling tower has the ability to do all sorts of things. It has air flows, and if you look at a building, there are cooling and smoke exhaust systems that exist in cooling and ventilation. What I really was talking about was this project that we're doing in Kuala Lumpur, 118-story building. We have 9 levels of parking. Now, parking garage normally has a ventilation supply air system. It has a ventilation exhaust system, and has smoke exhaust system. That building has 9 levels of parking with not a single fan, because what we chose to do is to position the cooling tower, which has this huge airflow, in such a way that it operates to ventilate the garage, and the airflow is large enough to meet all of the smoke exhaust requirements. So that kind of dual service is an innovation which can be used, and if push comes to shove, there's no regulation against it. The only problem in a city like New York is that a parking garage is usually in the basement, and the cooling tower can't go in the basement easily because of the exhaust requirements. But where you have the ability to be creative, you can think about a lot of creative things for cooling towers. So, cooling tower is a lot of fun. And I hope I've given you a little bit of an insight into the subject. If there's any comments, questions.
Okay. I have a question. You have a question there? If you want to go up to the other microphone while you're doing that. Is there a difference whether it's a residential structure or commercial or a hospital? Does it change?
No, they all work the same way.
Okay.
It's all the same.
Okay.
You'll find that there's water-cooled equipment in residential structures is far less, there are far fewer water-cooled systems in residential structures. I mean, they exist, and there's enough of them around, but it's far, far less common than you would find in commercial buildings or in hospitals. But the cooling tower works the same regardless. I mean, it's exactly the same if the cooling tower was being used for an industrial application, like, for example, cooling some machinery or what have you. Yep.
Hi, my name is Walter Jones. I'm the Director of Operations for M. Rappaport Company. We manage commercial properties. You mentioned about the difference between water-cooled units with a cooling tower compared to an air-cooled system, air-cooled package unit. On a 90-degree day, the biggest difference in terms of operation is the energy that's used to disperse the heat from the air-cooled unit compared to the water-cooled unit. Because we have a big difference in my office. Should we get a water-cooled package unit for some tenants, or should we get an air-cooled? Is there any other factors outside of that on a 90-plus day that I should be concerned with?
Okay, yes, and I think we'll start the lecture now. It'll go about an hour. The deal is this. From a factual point of view, the water-cooled equipment is more efficient and uses less electricity and is less costly on a long-term basis than air-cooled. However, there are any number of issues that come into play. There's the financial objectives. I mean, you go and you take a look at a residential building that's being built on a speculative basis. The guy wants to get the system in, operating, and he wants to get out, you know. So he doesn't care about long-term finance. As soon as he gets the thing done, he's out, and so his objectives financially are not consistent with energy conservation. Can you fit a water-cooled equipment in? I mean, getting a piece of water-cooled equipment in a location is fine, but then you have to be able to connect it to water-cooled. Do you have a place for the cooling towers? Will it fit? Won't it fit? Air-cooled equipment has a lot of flexibility. You can set it in a building. You don't have to have it at a place where everything is discharging. What about the discharge from a cooling tower? Where does it go? Does it go, for example, does it present an annoyance to a tenant who has a window open to a playground area, to a terrace area? There are any number of factors that play into the equation of what you should use. However, the point I was simply making was that from an engineering efficiency point of view and from a long-term ownership point of view, water-cooled is always more effective. And that's the reason why there are so many water-cooled systems around. But there are hundreds of factors which can be applied depending on the objectives you're looking at. So in the debate, water-cooled is more effective. Tell me why I can't use it.
Okay, thank you.
All right.
Herschel Weiss is Shokin Water. What is, you said 2% makeup? Was that the amount for the efficiency on most towers?
Oh, yeah, well, you know, what happens is that the amount of water that has to be made up in a system consists of, number one, the amount of water which is evaporated in order to reject the particular BTU load. And then on top of that, none of these systems are perfect so that only only vapor goes out, evaporated. There's always a little bit of drift. You have little minuscule droplets of water that are carried over. That's a carryover that has to be done. And in addition to that, as the water evaporates and leaves the solids behind and the solids build up, you get to a point where the solids will begin to impact the overall water chemistry and stability. So you have to blow off some water. There are lots of, I mean, you can do a detailed calculation on a specific tower for each of those components, but notwithstanding, for the purpose of an illustration, I selected 2%. Some people would say, you know, 2%, it could be 1.75%. Other people say, oh, we have to use 3%. All of those have validity in particular cases, but I just used the 2% of the circulating water as the factor, and that's a very common number.
And that number includes the blowdown?
Yeah, for a relatively decent water. I mean, if you are in an area where the water that you're using for makeup water has an extremely high solids content, like, for example, recycled sewage in terms of gray water, then the blowdown rate would go up.
Thank you.
Okay, that's it then. I'm going to be around for a little while before I run away. So if anybody has any other questions later, you can catch me. Or if you need to ask another question, Margie can tell you my telephone number. And I'll be happy to answer any questions. Okay?
Absolutely.
Thank you.
Thank you. Thank you, Valentine. That was excellent. That was excellent.
You already understand that this Legionnaires disease bacteria was first identified in Philadelphia in 1976. It was the bicentennial year. The Legionnaires came in for a 3-day convention. It ended in July. Starting in August, people started to get sick. 221 sickened, 34 died. At the beginning of August, the CDC started to conduct what would be one of the largest disease investigations in their history. They sent 30 epidemiologists, microbiologists, and other investigators to Philly to try to investigate. And finally, in January of '77, they associated the bacteria with the disease. A lot of this information, and in the interest of brevity, I'm going to focus on a couple of things here. This comes from ASHRAE Guideline 12, which is the definitive source when you want to get down to the actual system. What do I have to do in this system, right? Hands-on, you know, where the rubber meets the road or where the water meets the pipe. What do I have to do? You'll go to ASHRAE Guideline 12, and ASHRAE's 188 standard refers back to Guideline 12. This is what I'd like you to take away from this slide. You've heard today that this is a ubiquitous bacteria. It is everywhere. If I find it as 6 colony-forming units, 6 CFUs per ml is the measure, let's say. If I find it at 6 in a cooling tower, it's not a cause to scratch my head and say, how did it get there? Our job is to keep the numbers low. We want to make sure that it doesn't get amplified, which happens from warm, moist environments. It doesn't get disseminated like when you aerosolize it and push it into the air with a cooling tower, or transmitted like drifting down the street. And another comment with transmission is a lot of ASHRAE Guideline 12 is about design. You know, you don't put an air intake near a cooling tower, things like that. That goes to transmission. And then, I didn't hear this mentioned, so I'll mention it now. A big part of an audit is looking for dead legs. A dead leg is a piece of pipe, there's no flow through it. It could be in a cooling tower, it could be in a hot water system. The toll taken by Legionnaires' disease. This number is the range is so wide, 8,000 to 18,000, because we believe it's very highly underreported. And I believe that this is even the CDC's number. So it's not me in the last 2 minutes throwing a slide together saying, well, make it a wide range. This is really what they say. The death rate, though, you'll see varying ranges from 5% to 15, some as high as 30. The higher end are those that are associated with facilities that have people with compromised immune systems, and older people as well. One note here is for people associated with the management of properties, but not hospitals, bear in mind that compromised immune systems could bring in large populations of people into a building, even though it's not a hospital. It could be an infusion center for chemotherapy. It could be some kind of a treatment center for other diseases that are associated with compromised immunity. So it doesn't have to be a hospital. The danger in this bacteria gets amplified, is magnified by these three processes: amplification, dissemination, and transmission. But the bacteria itself is everywhere. It's in the air, soil, and water. And if we treat it conscientiously, you're going to be able to control it.
So thank you so much for coming. Have a good day. Thank you.